Hello, so in this video we are going to be looking at reversible reactions and what reversible reactions are, and then we're going to move on to equilibrium, which is a state these reversible reactions can produce, and looking at some of the conditions that can change. So on the board, or on the screen should I say, there is an equation. We've got magnesium plus oxygen makes magnesium oxide, and the key about this equation is either the magnesium or oxygen will run out first, probably the magnesium, and then magnesium oxide will stop being produced. The reaction will be complete, and that's one type of reaction. One of the things runs out and the product stops being formed. You can have different types of reactions though, so if I was to write out the equation where we've got nitrogen reacting with hydrogen, you get ammonia being produced. So that's 2NH3. So in this reaction it's a little bit different, because as soon as nitrogen and hydrogen react together to form some ammonia, as soon as it is produced, is able to decompose, so it's able to go back to the nitrogen and hydrogen. So we can go that way and we can also go that way, which is why I need to redraw my arrow, because we draw these types of reaction where it's reversible, it can go both ways, like that. So this is showing that nitrogen and hydrogen can produce ammonia, but ammonia can also produce hydrogen and nitrogen. So this is a type of reversible reaction. Now, if we were to keep this reaction in something called a closed system, now that means that our temperature, the pressure can't change. If it's in a closed system for long enough, the rate of that forwards reaction going that way would equal the rate going that way. So when the rate of reaction going forwards, so these reactants producing this, the time it takes the rate of reaction for these to react together and form this are equal to the rate of that, that's when we get something called equilibrium. So that is one of the key words today, and that's when the rate of reaction for the rate of the forwards reaction is equal to the rate of the backwards reaction. And I've got that on the next slide, so if we just scroll down, I've got a way of explaining it in some ways, a kind of real life analogy. So say this man is on a down escalator, he's decided he needs to go back to the top, he's turned around in the middle and he's running up the escalator, and at the minute he's stuck in the middle, and the reason he's stuck in the middle is because the speed at which he's running up is exactly the same speed that the escalator is going down, so he's actually going to get stuck. And that's the same as equilibrium. You've got the speed, or the rate, should we say, a more scientific way, the rate of the forwards reaction equals the rate of the backwards reaction. So it's all to do with that backwards and forwards reaction. So rate of forwards equals the rate of the backwards reaction. And that's just a way of remembering it. The speed at which the person is running up equals the speed at the thing going down. That's when that man has reached equilibrium on the escalator. Same idea here. The rate of the forwards reaction, the rate that the reactants are reacting together, is equal to the rate that the products are reacting together. And you form something called equilibrium. Now, in equilibrium, there is something like I talked about earlier, closed system. It has to be a closed system, because as soon as the system is changed, things are going to happen, and we're going to look at that. So French scientist here, Le Chatelier, is someone who looked at equilibrium and what happens when those systems change, and he says here, if a change is made to the system, this system responds to counteract the change. So that's quite a mouthful. And basically what it's saying is, if concentration, temperature or pressure are changed, so any of those three things change with an equilibrium, the forward and backwards reaction will no longer be equal. So actually they'd be happening at a different speeds to each other. The rates would be different. So to counteract that, things are going to have to happen to the forwards and the backwards reaction. If I just write out H2 plus, I think it's 3, NH3. If I just write that out for now, just to show you. So for example, if something was to happen here, one of the conditions changed and therefore the forwards reaction was not equal to the backwards reaction, what's going to have to happen is we're going to have to change something. So temporarily things will change in this system until that equilibrium, the rate of the forward reaction, the rate of the backwards reaction can then be equal again. So if we look at it as specifics, because when we look at it generally it's kind of hard to understand. So I'm going to get this, I've got this equation here and I've got 4 questions based on concentration. So in this video we're going to look at the concentration and how Le Chatelier's principle looks at concentration. So concentration was one of those key things that if it was in a closed system it would be alright. But as soon as the concentration is changed, that can cause impacts for the equilibrium. So in my diagram here I've just drawn out some of the elements. I've drawn out the reactants here, products, reactants and some products. And it could be going either way. It could be that these are reacting together to form these two, or it could be that these two are actually reacting together to form this. So it's either the reactants reacting to form the products, or the products in this case reacting to form the reactants. And the first question here says, what happens to the system if the concentration of the reactants increase? So what happens to the system if the concentration of the reactants increase? So I'm just going to get a blue pen to add some more of the N2s and H2s. So now that we've got more of these reactants, I've not added any more products because it's just saying about the increase in concentration of reactants. I've added some more reactants to the system and then I've made it a closed system again, okay? What happens is that more of these can be colliding. Therefore, the rate of reaction, the speed at which these can collide and form the product increases. So temporarily, the forward reaction would increase. Then, so temporarily the forward reaction would increase until equilibrium is reached again and they're balanced, because eventually these will start to increase and then it'll get back to that equilibrium where the rate of the forward reaction equals the rate of the backwards reaction. So we just look at number 2 and then I'm going to ask you to pause the video and do 3 and 4 yourself and then we'll go through them. So question 2, what happens to the system if the concentration of the products increase? So I'm just going to rub out those extra ones that I just drew and I'm going to add in red the products, because this time is if the products increase. So NH3 and then NH3. Got the N. So now there's more products in here, so they can react. There's more products for them to collide, so therefore they're more likely to collide. So the bigger reaction is going to be the backwards reaction, because these are going to be colliding at a greater rate because there's more of them. So here you would say, I've not got much space to do it, but I would say the backwards reaction is favoured because there are more particles colliding on this side. And the key idea here is it's not a permanent change. Equilibrium will be eventually reached once they get back to the same levels. So they're back to the fact that the rate of this reaction is equal to the rate of that reaction. So eventually things will balance back out. So the particles are colliding and reacting at the same rate as for the forwards and the backwards reactions. So if you just pause the video and have a go and think about what would happen to the system if the concentration of reactants decrease. Imagine rubbing some of these out and have a go at it, and then come back and look at the answers and see what I've put. Okay, so I'm just going to rub these ones out because they were from when we had the extra products, and I'm also going to, for this one, add out the remove these reactants. So now if you look at my closed system here that I've just created, I've got more particles that are products. Therefore, they're more likely to collide, so they're going to have a bigger rate of reaction. So the increase in rate of reaction is going to be the backwards. So temporarily, it's going to favour the backwards reaction until those reaction rates are equal again and equilibrium is reached. So if you've written anything about the fact that to start with, the backwards reaction will be happening faster because there's more particles colliding until it reaches equilibrium again, you'd get the mark. Question 4. What happens to the system if the concentration of the products decrease? So if I just get those back and I rub out the products, it's clear to say that these ones, there's more particles colliding here than there are products, so the reactants are going to be reacting really, really quickly. Lots and lots of collisions, therefore a greater rate of reaction. So these are going to be produced at a quicker rate. So the forwards reaction will be favoured before equilibrium is reached again. So it'll be shifted towards the forward reaction until the equilibrium is reached again. It's a temporary change. That's what needs to be really, really clear. It's not a forever change. Equilibrium will be reached again.